Hello everyone, welcome back to the lecture. We'll talk about some artifacts and through some examples, we try to explain the design principles for precision machine design. So, as I mentioned in the last lecture and try to ask which one is better. If we consider these designs, table design with 3 legs and 4 legs, sometimes we have many legs. So, if we consider design principles or design of precision machines and think about the repeatability part and the precision parts, which one is better? So, we'll try to understand through this example. So, what we see this three-legged table called many times we call it coffee table. There are many examples and it's like we can find it in every home. One thing what we realize that these tables, they don't rock, they are quite stable, and that's the reason means uh, in houses, even in garden, in different places, if we are not sure of the surfaces, we can take them and put them, and we can quite easily put things on top of it, and more or less they are stable. So what is the reason? So let's try to understand. So if we consider three-legged table, what we see, what is important to understand is the three supports we have at the bottom. And if you connect them, so with the 3 points, we can always define a plane surface. So what happens, wherever we put this table on any surface, we always define a plane surface on the ground and also a plane passing through the 3 contact points on the table, and these two planes are always conformal, and that's the reason they don't rock, they are stable. So it's a very important to understand that if there are three contact points, they will define a plane, a surface, and that's the reason it's always stable. On the other hand, if we talk about four-legged table, what is the problem or what are the issues with this? So, in this case, what we have is 4 contact points. So, if we want to put the table on a level surface and moment we move it, we might have encountered every time we move a table, four-legged table from one place to another place, we always have to find a surface or we have to do some adjustment. And why we have to do is because the surface passing through these 4 points may not align exactly to the surface, to the ground, and that always gives a problem, and many times we have to do some adjustment. We try to put something, some paper or some wooden chips or to get the right height so that we can avoid rocking. But what is the inherent problem in these kind of designs? So I think it's very important to understand that part so that we understand that how this knowledge or the understanding can lead us to design even the table for ultra precision motion stages, how to support them. So let's just walk through this. So now what we understand that with 3 points we can always define a plane. So now we have 4 contact points. So if we want to define a conformal surface, or suppose plane surface, it's very important to have all the 4 points on a single surface. So it puts a lot of constraint on the design and manufacturing. So what we can, so first try to understand what happens if we take just 4 points, general 4 points. So now what we realize that in this case, actually there are 4 independent surfaces defined, and in order to work properly, all these 4 planes should be coincident, and it puts a lot of constraints on the design. But at the same time, what we do realize that if it's for some precision application, if you will want to put a very sensitive instrument or any kind of setup on top of it, it puts a lot of manufacturing constraint to it, and how it can be resolved if we use kinematic design principles. So knowing that now is there are 4 surfaces, and moment we move it to different surfaces, different place, different location, we have to make sure that the height of these legs, the length of these legs, the surfaces, they should all be perfect in that sense. So what we also realize with experience, that whenever we move a new furniture to our houses, what we usually do is, wherever we want to place it, we place the furniture there, the table there, and we try to put loading on top of it. What it does, so exactly what it's doing is, moment we put the load, we are dependent on this movement, so diagonal movement. So we are relying on diagonal compliance. So moment the tabletop is compliant, it has a diagonal degrees of freedom, it may be fine, because what happens, moment we move it to different location, then it deforms and take the surface. So that way it works. What we realize, that because of that, the top surface now get deformed, and it means anything we attach on top of the surface, on top of the table, that will also get affected. The measurement, everything will get affected because of that deformation. So we should be aware of that. Moving to next example. So I have asked about this example, and many times we have seen this chula, clay chula in our houses. It's made of mud or bricks many times. So if you are talking about this, so if we look at it closely, and the chulas which are made by our grandmothers, who has a lot of experience making this kind of chulas, and they also cook, make things on top of it, so they understand how this should be made and how many supports should be there. On the other hand, if we look at this modern chula, the gas burner tops, usually we have again 4 supports. And again, what we try to understand, what we see here, and I mentioned earlier also, that the elements of precision machine design is already there. Through experience we learned, and we try to implement in our systems, but somehow it's lost, or it may not be in place in a systematic way. So suppose if we want to design something and from scratch and want to implement this kind of thing, many times it's a lost, or we need a very experienced person to take care of those things. So, for instance, if we try to understand this design, so in the traditional chula, as I mentioned that if we look at these chulas made by our grandmothers, mainly the elderly people, they only put 3 supports. So, what we see here, only 3 supports here. And if we try to look back and try to understand the geometry with the 3 points, what happens is any kind of utensils we put on top of it, it will be stable, it will not rock, whether it's some kind of spherical surfaces or even the flat surface, they will not rock. And that's the reason we see many times these tripods, because they are stable. Moment we have a four supports, we have issues, and what we see is, in this case, we have some rubber mountings and we see a lot of chatter. So, yeah, many times we have this kind of support here also. Sometimes they make contact here, and if there is some issues, some tolerance issues, we will have a problem and we can see some kind of chattering, some noise. So, not very stable. Unfortunately, these modern designs are also translating into our older designs, because now we have started copying it blindly. So, therefore, it's very important to understand that what are the principles, guiding principles, and whatever learned through the experience, many times it works and we should be able to implement those things in our designs. So, yes, we try to understand through very simple examples the kitchen top, chulha, or the table design, and try to understand what is the importance of kinematic design, and we'll elaborate more on that. So, how it will be translated to any precision machine design, we'll take some more example. So, suppose if we have this block and we want to support against the wall, against the 3 walls, I think the usual way is to just talk about the tolerances, and the perpendicularity we'll talk about, and try to rest against the surfaces, 3 surfaces. So, that is the usual approach. And many times when we are talking about precision machine design, we resort to precision components, and we define very tight tolerances for each and everything. I think what we realize that if we understand the kinematic design or kinematics, we may not have to do that. And just by defining the contact points, we should be able to constrain it properly. And then what we have to emphasize is to focus on designing those contact points or contact surfaces. So, if we see here, the 3 contacts at the bottom, if we connect, it defines a plane. So, what happens if we put this block on that surface, on the horizontal surface, actually it makes contact with those 3 points, and we get a plane surface, and it can move on that horizontal surface. So, of course, that those 3 points, if they are the reference point, they define the horizontal surface, and it can slide. So, it can slide in both directions, it can move in this direction, it can move in this direction. So, call it x and call it y. So, what happens if it's on the surface, and if we, so it can slide and it can rotate also along the z axis. So, if we move along x, what we see is it will first make contact with one point, any of one of them, and then it can start rotating along the z axis and then make contact with the other point. and that's how it also. So with the 2 points actually is also constraining the z rotation. So only way now it can move is along the y-axis, which is this. So as we move along the y-axis, the contact against this wall will be made and it will be completely constrained. Of course, what is the assumption here? What we try to highlight here is that this contact should be made all the time, should be there. So of course, we need some way to make these contacts possible, either. So what we later refer to is the nesting force. Some kind of nesting forces will be required, or we can use bolts and whatever is required to maintain that contacts. What we realize here is the location of this object with respect to the wall is defined. So we have to understand location versus clamping. So bolts are used for clamping, to put the two parts together, but may not be for location. It cannot define the location properly. So we need to understand how to locate it properly so that certain things or certain objectives, specifications can be achieved. So slowly what we realize that from this simple example, suppose if we are looking at designing CMM machines, so coordinate measuring machines, this is like very important these days, and if we are working in precision, every component has to be tested, has to be measured. So I think if you are aware of what you realize that it's sort of built on air bearings and there are granite table. So if we start looking at the supports, we'll see these things embedded in the design. And I think after this course, you may feel confident to design these kind of designs very easily. Some more examples, and for instance, for medical application, or suppose for some other application you want to design sensors. So in this case, it's for force sensing, and this is from my PhD work from Netherlands. So what happens if a flexible instrument interacts, and what kind of forces it exerts? So suppose if you want to characterize any kind of catheter or endoscopes or any kind of flexible instrument, when we manipulate these instruments and when they interact with the tissues, what kind of forces are there? So therefore, for the characterization, if you want to measure these kind of forces, it's very important that we should be able to measure it precisely. Yeah. Many times these forces are very small, so the setup has to be sensitive. It should be exact constraint, deterministic. So therefore, what you see here in these designs, if you look at it closely, again we have used 3-to-1 principle, which is used in machines in metrology to constrain the system. And later what we realized, this wire kind of things, we call it wire flexures. For the time being, we can assume that it's supported along those lines only. So 3 from the base, 2 from the other side, and the 1 from the other side. So that's why it's called 3-to-1, 3-to-1 configuration. And total 6 constraints are provided, and that's how the blue part, which is the sensing module where we mount the instruments and where we are interested. So we put we float it or we support it in this fashion. The wires here at the base, we can have the load cell here, which can measure the forces coming uh, along the length of the wire, and we can measure precisely what are the forces of interaction when these instruments are getting manipulated from the outside or when the tip is interacting with the tissues. So, this is like we can do the calculation and we will come again. So, forces, and so Fx is a force components along x, y, z and the moments, and these are the forces coming on the load cells. So, how it can be transformed, and is through matrices. And what we realize that if it's an exact constant design, it's very easy to write all these equations. So, we'll take these examples later and start with a very simple problem and then come to this, and then we'll try to understand how important is the exact constant design, so that one should be able to measure this kind of forces, or any, even with respect to the motion sensing we can understand, and we'll try to understand the benefit of these kind of designs. So, this is a setup where what I was talking about. So, there is a flexible instrument inside the glass tube, and at the tip we have this non-contact kind of cam, linear cam, and then is supported on air bearings, so that we can eliminate any kind of error or uncertainty we have. And when we manipulate, we rotate and move the instrument, what kind of forces are there, so that we can see. So, these are the details of the design, and I think at the end of the course everyone should be able to design or take up these kind of problems and do the design themselves. We'll take some more examples, and we'll try to elaborate more on these kind of artifacts. So, these are called kinematic clamps, which we'll talk about these things later. What we see here is there are groups. So, I have one here, and maybe we'll show in detail in videos later. So, here we have the groups and the a spherical ball joint, and they come in contact, and what happens, because of the design itself, the location is defined. So, I can put them together and it will go precisely to the same location even without looking at it. So, this is by design. I don't have to do any kind of adjustment. I don't have to I don't need any kind of external fixtures to enable and bring them together. So, that means they are concentric, but it's just by design. So, these features can be embedded in the design, it can be hidden somewhere, and moment we put it, we can see it's going to the same location all the time. Yes, there are some issues that we can discuss, but these are the principles, and that's how we can start. So, these are very old designs, and mainly used in optics. So, it's called kinematic clamp, even Kelvin clamps is called. So, again here you see 3 times 2, so total 6 contacts we have. There is another example. So, here I have a tetrahedron hole and a spherical and V and ball and flat end. So, 3 to 1 configuration again, and this also gives me the same kind of repeatability. So, any times I do, it will go to the same location, and I can definitely later clamp it, and I can it can be secure. So, these are the some of the principles we'll be talking about later, and we'll understand more, and we will be able to appreciate how better repeatability can be achieved in the machines. So, what we have to understand that in order to achieve precision, we have to change our thinking. The thought process has to change. There is a paradigm shift. We have to look at the architecture, how the components are assembled together, how how the tolerances, how the errors which are there because of the manufacturing constraints, manufacturing issues, even the limitations, there can be limitations, we cannot go beyond certain numbers. So, how those errors propagates, and we need to understand the overall architecture so that we can also clearly measure and see that what is the overall error of the system, what is the accuracy or repeatability. So, that can be calculate in the beginning itself based on the design concept, based on the configuration. What we also try to understand that degrees of freedom and constraint, they play a very big role, and that if we follow the kinematic design principle or exact constraint design, what we also understand that many of these things, the error might be there, but it's a systematic in nature, it will be constant and can be easily removed. So, and that way we can achieve very good repeatability even with the components which are not having very tight tolerances. So, precision doesn't mean precision component. Precision means deterministic behavior. How we can bring, in a way, you call it transparency or accountability in the system. The way it's designed, the way the different parts placed together so that it's identifiable, the errors can be measured and can be compensated. And of course, later we'll move to flexures, and that here we are talking about the contacts is a friction base, but slowly we'll try to remove the friction part as well. We try to remove contacts with the suitable flexures, and we should be able to achieve high precision instruments or machines. Thank you.